This is Unit 3, Block 3. I'm going to do question number 5 on the Mom Computer Practice Assignment, and your problem should be fairly similar. So in number 5, you're given a graph, and it gives you the formula of that function that's graphed. And my problem, it's asking to find the interval where the function is concave down. Yours may ask, find where it's concave up. Perhaps you even have questions where it asks where the inflection point is. If you want to understand where a function f is concave up or concave down, or find its inflection points, then it means we need to first find the second derivative. The second derivative helps us understand the concavity of the function f. So I'm going to have Excel help me with some of this. And again, I recommend that you do use Excel as a tool to check your work and use Solver and so forth to solve for some of these points. On Word, when you're write-ups, you will have to write it all out formally, but you can do a lot of the busy work in Excel. So I have created an Excel file. Let's just start over here. I noticed the graph they gave me spanned from x equals -3 up to x equals 5. So that's where I started when I made my Excel file. I had x equals -3 up to x is 5. I then put the function f of x in there, right? On their function, they had x to the 4th divided by 2. That's the same thing as 1/2 times x to the 4th, or 0.5 times x to the 4th. And here's the rest of the function. I just put that in there. I also put in column C, the derivative, f prime. And then I found the derivative of the derivative. So let's just quickly look at that. The derivative of f. If f was 0.5 x to the 4th, when you drop the 4 down, 4 times 0.5 would be 2. And then you'd subtract 1 from the exponent, so 2x to the 3rd. 1.5 x to the 3rd, to find the derivative of that, we drop down the 3. 3 times 1.5 is 4.5, and then we subtract 1 from the exponent, so it's x squared. And the derivative of 7.5x squared will be 15x to the 1st, or just 15x. And now to find the second derivative, I start with f prime and I find its derivative. So the derivative of 2x to the 3rd is 6x squared. The derivative of 4.5x squared is 9x. And the derivative of 15x is 15. All right, so I put those functions in. And again, we are being asked to identify where f was concave down. I'm actually going to just do a little more than that, which will serve as some review. I'm going to also just add complete descriptions of what's going on with the function f. So let me zoom this out a little. First, let's focus on column C, the derivative values. Remember, when the derivative is negative, that tells us f of x is decreasing. So here, derivative negative, f of x decreasing. Derivative negative, f of x decreasing. Now, when x is -1, we see the derivative is positive 8.5. So that means f is increasing. Let's look at the graph of f over here and see that. X is -3, f is decreasing. At x is -2, f still seems to be decreasing. But by the time you get over here to -1, f is increasing. It's going up again. So in between -2 and -1, a change occurred. There's a local minimum in there. The derivative changed from negative to positive, so there must be a local minimum in there, somewhere between -2 and -1. All right, then the derivative at x equals 0 is 0. And that's a critical point, right? And then at x is 1, the derivative is negative, so f is back to decreasing again. So at x equals 0, there's a critical point. On the left side of it, the derivative was positive. On the right side of it, the derivative is negative. So f was increasing, then flat, then decreasing. All right, then we have derivative negative, 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 all through this span. So f is decreasing, decreasing, decreasing. That's this big span here from x is 0 over to x is 4-ish. The derivative's negative, so f is decreasing. And then at x is 5, the derivative's positive, so f is increasing. So you see that makes sense. At x is 5, it's going up. Okay, so that's what we can take from the derivative. Now let's move on to column D, the second derivative values. Remember, when the second derivative is positive, that tells us f is concave up. So I'm going through and looking at my second derivative values. Here it's positive 66, so that tells us f is concave up. Let's look at that. At x is negative 3, that's right here. It says the second derivative is positive, so f is concave up. That makes sense. Right over here, f is concave up, like a right side up bowl. And then still at x is negative 2, the second derivative is positive, so it's still concave up when x is negative 2. Yep, it is. If you look at the graph, it's concave up. And then when you hit x is negative 1, the second derivative is 0. So that's a possible inflection point, but we know when we look at the actual change that occurs, we know it is an inflection point because at x is negative 1, the second derivative changed from being positive to suddenly being negative. So that means f changed from being concave up to suddenly being concave down. So you see it was concave up before that point, concave down after that point. Second derivative positive, then suddenly second derivative negative. So that's an inflection point at x is negative 1. All right, and now the second derivative is negative here. And now notice that x equals 3, suddenly it's positive again. It's negative when x is 2, and the second derivative is positive when x is 3. A change occurred there. Let's take a look at the graph. X is 2. It looks like it's kind of concave down, like a upside down bowl. But when you get to x is 3, it's right side up, like a right side up bowl. Somewhere along this span, the change occurred. The inflection point happened. But it seems that it happens at a decimal value somewhere between x is 2 and x is 3. So we could solve where the second derivative is equal to exactly 0, and that will identify that point exactly. So you can use Xsolver to do that, or you can do it by hand by setting this second derivative function equal to 0 and using either factoring or the quadratic formula to solve. I'm going to do it with Solver. I put my cursor here near the place where the second derivative is 0, so maybe here or here, either one. I go to Data, Solver. I want it to set cell D8 to a value of 0 by changing this x value cell. I want it to find the x value that makes the second derivative 0. I hit solve, and that's pretty close to 0. That's just scientific notation there. So it seems that it's 2.5. When x is 2.5, the second derivative is exactly 0. Notice on the left side of that, the second derivative is negative, and on the right side of that, the second derivative is positive. So this is an inflection point. Inflection point at x equals 2.5. So there's an inflection point at x equals 0, and also an inflection point at x equals 2.5. Inflection points occur where the second derivative changes sign, changed from being positive to negative. And then the other inflection point, second derivative changed from being negative to being positive.